So we'll continue with the example of the housing data. The problem is, what is an average house price in Kitchener-Waterloo given the size of the living square space, which is measured here in square feet? And here is a scatter plot. We have the floor space on the x-axis and the price of the house on the y-axis. And you will see there are some houses that are very, very large. Most of them are over here, but some of them are very large. So the question for you, is a straight line a good choice here? And you see the four corresponding answers. So I will leave you to think about that and carry on to the next page. Now I think I'm restricting just the floor space to the smaller ones, up to 4,000 square feet. See, I'm just looking at this here, over here. And for this subset of the data, I have another question. What can we say about the variance as x increases? So what is the variance of price as x increases? So as the floor space increases. Do we see more variability as the floor space increases in prices, or roughly the same, or decreasing, or more complex? Well, again, I will leave you to answer this question, and carrying on. The goal is, in linear regression, to fit that regression line, right? And to do so, we have to choose values for alpha and beta. We've seen the model is y equals alpha plus beta x, and we have to find values for alpha and beta. We also have sigma to worry about. So we've already mentioned that we've derived maximum likelihood estimates for alpha and beta. And so if we believe maximum likelihood is a good criterion, then the problem is solved. And the actual specific solutions are over here. This is not meant for memorization. This is meant for completeness. So these are formulas you have seen in Stat 231. Later, after the review, we will derive maximum likelihood estimates for linear regression with more than one x variable, and which will turn out to have generalizations of these formulas, but not in exactly this form. And so I have to think about these formulas too, so I don't remember them offhand usually. So it turns out that the solution to the maximum likelihood approach here for linear regression with one x variable is to minimize the square of the residuals. So residual is R. We're minimizing the square of residuals. And the residual is also y minus the fitted value, right? This is the expected or the fitted value. So when you minimize the square of the residuals, we have an expression for that, and it's called the least squares estimate. Least meaning minimize, right? Squares because it's squared, and well, it's an estimate. So it turns out that for linear regression, that the maximum likelihood solution is also the least squared solution, right? Because it happens to be that. That's only true for linear regression. Other types of generalized linear models don't have that. Freedom notation, R is the residual, and I have script R here, yi minus the estimated value, that is the estimated residual. The true residual that is unknown is epsilon here. And so you see I have taken the hats off here. So these are the true alpha values, the true beta values. So by true, I mean we're taking a sample, and the sample is of some large population, say all Canadians, And oh, we are in Kitchener-Waterloo, so it's all the houses in Kitchener-Waterloo. But we don't have information of the regression for all the houses. We just have a sample of 100 or so houses. And so these are the estimate ones. And the alpha and betas, the true ones, are the ones if we had all the houses in the data in Kitchener-Waterloo. Okay, so notation sometimes varies, so I'm using an RI instead of the hat over the epsilon I. Sample variance. So we have talked about alpha and beta, and here is the estimate of sigma. And there it turns out we actually have two estimates of sigma. The sample variance, the unbiased estimate, is this estimate where you divide by n minus 2. And that 2 comes from having to estimate two parameters in the mean structure, right? The alpha and the beta. So we lose 2 degrees of freedom. Just to look at them side by side, we have these two estimates, the sample variance estimate, where we divide by n minus 2. This is unbiased. This is the one we use. And the maximum likelihood estimate, which we divide by n. Of course, if n is really, really large, then it doesn't matter because it's sort of the same thing. The software implements this one. This is the one we use. Sigma squared is also called the mean squared error, MSE, and sigma by itself is also called the root mean squared error, or RMSE. So in terms of software, the slides use both Stata and R. Little more Stata than R. I use in my own work Stata. I don't use R. And so here's an example. So I'm clearing out the data. I'm importing a comma delimited file, CSV. I'm creating a new variable, generating a variable, and I'm rescaling it. And then I'm doing a regression here. Regress y on x. It's data used to have the y first and then all the x's. And here's the equivalent in R, where I have the read CSV file, same file. Then have to do an attachment here. And then the model has a slightly different syntax. So you have price as a function of floor space, specifying the data. And you need both the summary and the ANOVA command to get the equivalent of the regression command. All right, so when we look at the output here, this is the Stata output. You see I have highlighted 3 numbers, and those are the estimates of alpha and beta. Alpha is always given at the end in Stata, and here is beta, and sigma squared. By the way, the square root of this number, RMSE, is here, root MSE. This is the square root of that number. All right. And the corresponding regression output for R is here. And I didn't list the ANOVA table. I just gave the summary here. And so the estimates, the exact same estimates for alpha and beta are here in the reverse order, because in R, the intercept is listed first. So we have alpha here and beta there. And sigma squared is nowhere to be found on this output. I don't think. Yes. So, assumptions. With linear regression, we currently have only one x variable, but it will turn out to be much the same when we have more than one x variable. So we assume that the model is linear. That's an assumption. Maybe right, maybe wrong, but it's an assumption. We assume that the variance is constant as x changes. How do we know? Because the variance is here sigma, well, the standard deviation does not depend on x. Sigma does not change for x, it's always sigma. So we assume that the variance is constant. That may or may not be true in any one data set, and we'll later learn techniques of what to do if it's not true. But the regression model assumes it's constant. All right, so I've answered my own question. Non-constant variance means sigma would be a function of x. The distribution of the residuals is Gaussian, our normal. And because these things are fixed, and this is the only random element, then the distribution of y is also Gaussian. The residuals are identically distributed, which means we have the same equation for each observation, more or less. So there's no hidden x variable that we forgot to include that explains the outcome, but it's not in the model. And the residuals are independently distributed. So observations are independent from one another. We always assume that the techniques to deal with that are sort of advanced if they're not independent. So the x variable here, we haven't said nothing about it. It could be a continuous variable, so we can have a nice scatter plot. But it could also be a indicator variable 0, 1, or anything in between. The zero mean here is not an assumption, because anything that is not zero is just over here in the mean structure. So we have a linearity assumption, and we're only using 1x here. But given that the zero is not an assumption here. Okay, that concludes this segment.